In this video, we're going to explain the linear regression. We are first going to discuss an example that can be solved via a linear regression model. Then we are going to discuss the mathematical representation of a linear regression model and how this model can be actually solved and find the optimal coefficients of the linear regression based on the data. In this video, we're going to provide only the optimization in which we use a closed form solution to find the weights of a linear regression model. And in the next videos, we're going to provide a numerical solution to the same model. So let's first start with an example. Let's assume that we would like to rent an apartment in College Station. College Station, Texas is a college town. Therefore, the rent of the apartments varies. And some factors that, influence the apartment rent include whether the apartment has a big size or a smaller size, the distance of the apartment from campus, whether the apartment has a fitness or recreation center, pet policy, and all the things like that. So we can assume as part of this linear regression model that the output is the price of the rent, while the input are all the different variables, all the different factors that might affect the price of the apartment. Each of these factors, as part of the linear regression model, can be multiplied by a weight. And if these variables, these input variables, are of the same range, then the weight of each of these variables represents the importance, its corresponding importance. If we are to show this as part of only a one input, one output problem, in the x-axis of this figure, we can see one variable that affects the rent price, and this is the size of the apartment. And on the y-axis, we can see the actual output, which is the rent price. So if we have several pairs of data for which we know their size and their price of rent, then we can plot this data as these red dots that are depicted in this figure. Now we can see that these red dots have this increasing shape and imply that whenever the size of the apartment increases, then the rent of the corresponding apartment increases as well. We can also see a linear association between the size and the rent and the price of the rent, which signifies that a linear regression model would be a good representation between those two variables. Now, a linear regression model can be actually represented by this blue line, in this case of this one-dimensional input. For multi-dimensional inputs, this blue line is actually replaced by a multi-dimensional hyperplane. So this is also an example of some training data that can be used in order to find the unknown model parameters of our linear regression model. So in this case, our unknown model parameters will be the weights with which we multiply the variables of our model, as well as an initial bias term that reflects the bias of the output variable, the original bias of the output variable without the presence of any input. Now let's go ahead and see how this can be more formally formulated in a mathematical equation. So as an input for our linear regression model, we can have a d+1 dimensional space, which is represented by the input vector x. And we have d+1 dimensions because the first dimension is an extra term which corresponds to the bias term of the weight vector. And the next d dimensions represent the d features or covariates or inputs or predictors of our problem. In the case of our apartment rent prediction, this would represent all the attributes of the apartment that would be relevant to the final rent. Now the output, if we have a one-dimensional regression output, it would be represented by a scalar y, and this scalar y is also referred to as target, outcome, response. All these are valid terms. Now, the training data for the linear regression models are pairs of samples that represent different training data. In our case, different pairs of samples with attributes and rent prices from n different apartments. The model is represented by a function f that takes us from our d+1 dimensional space to our scalar output y. And this function f for the linear regression model has a specific equation because we assume a linear association between the input and the output space. We can also have this function be represented by this specific equation. So in this equation, W0 is the bias term, and then each of the attributes is being multiplied by a corresponding weight. Instead of having this algebraic notation of the equation, we can also have a vector notation where all the weights W have been accumulated into this vector, weight vector W, which has d+1 dimensions, and all the input features plus the extra bias term is being accumulated into this vector X, which also has d+1 dimensions. So if we take the inner product between the weight W and the vector X, we get exactly the same expression that we have originally assumed for our linear regression model. We really like to keep this vector notation because this will significantly simplify the calculations moving forward. So after we have gone ahead and formulated our problem and assumed a specific function that connects the input space with the output, we have to find a way in order to solve our problem. And in our case, this would mean to find the weights that would best represent our data and would best connect our input space with the output. Now, the most reasonable thing to do in order to do this is to minimize the prediction error. And when we say prediction error, we mean the difference between our input, so the difference between the actual output and the predicted output for a specific sample. Here, the square term should be outside the parentheses, and here as well. So the difference between our actual label and our predicted label can be referred to as prediction error. It's common for the prediction error to get its absolute value. And because the absolute value is usually difficult to handle in mathematical expressions, especially when we want to optimize functions, we choose here to take the square of this difference. The square of this difference is a term that it is easy to find its derivative, and it's also a term that is guaranteed to be always positive. Therefore, we don't have to worry about whether the predicted or the predicted value is less or greater than the actual value of each sample. We can see here this sum term that ranges from 1 to n, and this represents the different training data. So here, this prediction error is not only being computed for one training samples, but is being computed across our n training samples, and each prediction error is being summed. This is also the analytical expression of this same prediction error, where for f of x of n, we have substituted our regression equation that we have assumed from the previous slide, mainly the bias term and the linear combination of the weights multiplied by the attributes. Here, another important thing is that each sample xn, because it's represented by an input vector, it can also, by convention, we write each sample xn as first the term 1 that will be multiplied with the bias term W0, followed by each of the attributes of the nth sample. So xn1 represents the first attribute of the nth sample, and xnd represents the dth attribute of the nth sample. Now, because we would like to simplify our lives, and we really like expressions to be in vector notations, in matrix vector notations. Instead of carrying with us this large expression, we can actually simplify the same expression of the residual sum of squares into this very much compact expression that you see here. So in this compact expression, let's start with this matrix X, which represents the data matrix. So what this matrix has is that each row of the matrix has each of the n training samples. We have n capital rows because we have capital N training samples, and d+1 columns because each sample is represented by d attributes plus the one that corresponds to the bias term. Therefore, this matrix actually has all the values, all the attributes of all our training data. In the same equation of the RSS, this vector y represents the collection of all the labels of our training data. So y1 is the output of our first training sample, and yn is the output of our nth training sample. Finally, vector w, the same way we have seen it before, is a collection of all the weights of the linear regression model and the bias term in the beginning. So if we take this equation here and substitute all these terms, the data matrix X, the label vector Y, and the weight vector W, we further expand these equations, we are going to find exactly this solution here. So these two expressions are very much equivalent. Now, after we have done this, what we need to do is that we need to minimize the prediction error and essentially find the weights W that minimize the prediction error. In this equation, we understand that the variables y and x are already known because these represent our training data. Again, our matrix X represents our data matrix, and our vector Y represents the collection of all the labels of our training data. Therefore, the only unknown thing in this equation is the weight vector W. So we would like to minimize the residual sum of squares error with respect to W. And essentially, this will give us the optimal W for our training data. So let's see how we can do this. And in this video, we're going to explain how we can do this via a closed form solution. So our goal again is to find W star that minimizes our prediction error or our residual sum of squares. These two are equivalent. From calculus, we know that when we would like to minimize an expression, what we need to do is to find its first order derivative. We are also very lucky because RSS of W, and instead of E, this is written as W, RSS of W actually has a first order derivative. And we can actually go ahead and calculate the first order derivative of the residual sum of squares. So if we expand the expression of the residual sum of squares and then solve with respect to W, we are going to find this equation here. By expanding, we mean here that we're just going to multiply every element of this parenthesis with every other element of that parenthesis. Then we're going to sum terms that are the same. Essentially, these two terms here, this term and this term are the same. Therefore, we're going to sum them up here. And then we are left with this expression here. Now, after we are left with this expression, what we can go ahead is that we can calculate the first order derivative or the gradient vector of this expression with respect to W. And from calculus, again, we know that the gradient of this expression is actually this result. And this is because this first term does not depend on W, therefore we can remove it. This second term only depends on W itself. Therefore, the first order derivative with respect to W is just going to yield this number. And finally, this term is it just depends on W transpose W, which is going to yield this expression here. After we are done with calculating the first order derivative, we set this first order derivative to 0 and solve with respect to W. So after doing this, we find this closed form solution that is actually the solution of the optimal weights when we would like to solve for the linear regression problem. We have to note here that because linear regression is such a simple model, this is the reason why we can find a closed form solution. Normally, a closed form solution is a luxury that we really do not have. Therefore, we usually try to find approximate solutions through approximate optimization methods. Now, one question that we have here is whether the closed form solution that we just found, whether this is unique. And what we're going to show is that in the case of linear regression, because the optimization function has a very specific form, each solution is unique. And here you can find you can see in this slide, several examples of optimization functions that have several optima, which are local, have several local and global optima. And these functions actually do not have a unique solution. So let's start with one theorem that will help us to show that for the linear regression, for the prediction error or the residual sum of squares, we can find a unique solution. So based on this theorem, if we have an optimization problem in which we would like to find the minimum of a function f with respect to a multi-dimensional variable x, if f is a convex function and omega is a convex set, then any local optimum any local minimum that has been found for this function f with respect to x is also a global minimum. Essentially, what this says is that if f is a convex function, it will look like that. Essentially, it will only have one global minimum. And this will be a potential shape of a function that is non-convex. So how we can use this? We can use this by also in combination with the second order derivative test, which states that if the Hessian matrix of a function f of x is positive semi-definite, then f is convex. Now, if we have a function f of x, which is based on a multi-dimensional space x that belongs to a d-dimensional space, then its Hessian matrix, essentially its second order derivative is a d by d matrix. And from this second order derivative test, essentially if the Hessian matrix H is positive semi-definite, then f is convex. The definition of positive semi-definiteness is this. And what this means is that H of f is positive semi-definite if for every vector u, then this product u transpose HF u is greater or equal to 0. And essentially here we show two examples of a convex and non-convex function in the multidimensional space. So we are going to leverage these two in order to show that the RSS error for the linear regression has actually a unique solution which corresponds to a global minimum. Again, let's remind ourselves here that this is the expression of the RSS error. This is the expression of the first order derivative as we have calculated before. And what we need to do is find the expression of the second order derivative or else the Hessian matrix of the RSS error. So now if we take the first order derivative of the gradient of RSS with respect to W, we're going to get only this term 2 multiplied by X transpose X. And we get this by just computing the second order derivative of this expression with respect to W. We also have to note here that the Hessian is a D+1 times D+1 dimensional matrix, and we can actually validate this by doing the calculations between X transpose and X. So X is a matrix that has n rows and D+1 columns. Therefore, its transpose will have D+1 rows and n columns. So when these two are multiplied, they will be D+1 times D+1. And similarly, the gradient vector of RSS is going to be a D-dimensional vector. And if you follow exactly the same logic and try to find the dimensions of all these components, you will see that the final dimension is actually a D+1 dimensional vector. So what we need to show essentially is that this Hessian H is positive semi-definite. Based on the second derivative test, the only thing that we need to do is that we need to show that for every U, this expression holds. And this is what we're going to do here. So for every U that belongs to the D+1 dimensional space, we compute this expression here. When we substitute H and expand this expression, then we can find actually that this thing here is basically always greater or equal to 0, because this X times U is the L2 norm is always greater or equal to 0. Therefore, the Hessian of the RSS error is positive semi-definite, and those RSS of W is convex, and therefore any local minima is a global optimum. So this means that the solution that we have found, these ordinary least square solutions that we have found from the previous slides, is actually a global minimum of the RSS error. So what we have said so far is that the linear regression can be solved by using as an optimization criterion the prediction error, which is the square between the square of the difference between the actual label and the predicted label of the data. If we do the calculations, we can actually go ahead and find a closed form solution closed form solution of the RSS error with respect to the weights of the linear regression. And this closed form solution is actually unique. So in the next videos, we are going to see how this, instead of solving this problem with respect to W, we can actually approximate this problem using approximate optimization methods. Finally, what we have here is a simple question in which we assume this nonlinear regression model. So this nonlinear regression model has two variables, x1 and x2, and three weights, w0, w1, and w2. So we have a set of training data here. And the question is whether this RSS error essentially has a global minimum, a local minimum, and why. So the first option here is that we do not know if RSS has a global minimum with respect to W. The second option is that RSS has a single local minimum with respect to W, which is also global. And finally, the third option is that this depends on the training data. So what we can see here is that this RSS error with respect to W0, W1, and W2 has actually not changed much from the RSS error that we have seen. So again, we have the same expression with respect to our weight parameters, W0, W1, and W2. The only thing that has changed is that instead of having n different attributes. Now we only have one attribute, and in the first factor, this attribute is being contributes only on its own, and in the second factor we have the square of the same attribute. However, this xn and xn square are actually part of our data. They are not unknown variables. Therefore, with respect to the unknown variables W0, W1, and W2, we actually still have a linear regression problem. Therefore, basically, based on what we have proven so far, RSS is a convex function with respect to W, because the only thing that has changed is the data matrix rather than the weight vector.